So now that we've got utility defined and we've got this pi star defined, we can actually do an even better job of writing out pi star. And let me do that. All right, so does this equation make sense, Michael?
Let's see. So the policy, is that a star
Yep,
again, or is that a
that's
K?
a star. So it's the
Okay.
optimal policy.
All right. The optimal action to take at a state is, well, look over all the actions and sum up over all the next states. The transition probability, right? So that's like the probability that we end up in state S prime.
Mm-hmm.
And now we have the utility of S prime. The problem being that that's not defined.
Well, it sort of is. We've defined it immediately above, at least with respect to some policy.
Yeah, but that's concerning because we don't know. I mean, the policy that you want to put in there is got to be the policy that you're trying to find.
Right. So, in fact, implicitly, what I mean here is pi star. So,
Yeah.
in fact, let me write that down. That whenever you see me write from now on the utility of a state, I'm almost always going to actually mean the utility of the state if I follow the optimal policy. We might call this the true utility of a state.
I see.
So I'm just going to write this off to the side here as something for you to remember. So this says then that the optimal policy is the one that for every state returns the action that maximizes my expected utility.
With regard to the optimal policy, it feels rather circular.
It is rather circular, but you're a computationalist. You're a big fan of recursion. We just went through a whole exercise where we figured out the geometric series by effectively doing recursion.
It's a similar kind of situation for this?
It kind of is. So let me write one more equation down, and then you'll be one step closer to actually seeing it. Of course, if we're in an infinite horizon with a discounted state, even though you're one step closer, you won't actually be any closer. Well, let's worry about that when we get there. So let me write one more equation down.
We're never going to get there. It's infinitely long.
Yeah.
Wait, are you demonstrating something with this lesson by making it infinitely long? We keep.
I'm certainly demonstrating something with this lesson. I don't know what it is. So let me write this next equation down. So then the true utility of a state, S, is then I'm just basically going to unroll the equation for utility. It's the reward that I get for being in that state, plus I'm now going to discount all of the reward that I'm going to get from that point on. Got it?
All right. So once we go to our new state S prime, we're going to look at the utility of that state. Okay, that's sort of fine. Modulo the recursion. We're going to look at over all actions, which action gives us the highest value of that. Oh, I see. That's kind of like the pi star expression just above.
Yep.
Then, all right, so once we figure that out, we know what action we're going to take in state S prime. We're going to discount that because why? Because I guess that just kind of ups the gamma factor on all the rewards in the future.
Right.
And then we're going to add to that our immediate reward. Yes.
Right. So
okay, I think I follow
yeah,
that.
so in some sense, all I've done is I've kept substituting pieces back into one another. So the true utility of being in a state is the reward you get in that state plus the discount of all the reward you're going to get at that point, which, of course, is defined as the utility you're going to get for the states that you see, but each one of those is defined similarly, and so the utility you'll get for S double prime, say, will also be further discounted, but since it's multiplied by gamma, that'll be gamma squared, and then S triple prime will be gamma cubed, and so that's basically just unrolling this notion of utility up here.
Okay, so now it seems like all the pieces are in one place.
Right. And so it would be nice if we were done. And I'm going to say that we're not just one step closer, but you can see an oncoming light, and it is not an oncoming train. Okay? So
yeah, this seems like a really important equation.
It is. In fact, it's so important it's got a name. You want to guess what the name is?
Bill.
That's actually very close. It's Bellman. It's Bellman equation.
Bellman equation.
Esquire. This equation was invented by a guy named Bellman, and it turns out to be, in some sense, the key equation for solving MDPs and reinforcement learning.
Wow.
And it's actually even more subtle than it looks. But basically, this is the fundamental recursive equation that defines the true value of being in some particular state. And it accounts for everything that we care about in the MDP. The utilities themselves deal with the policy that we want to have. The gammas are discount, all the rewards are here, the transition matrix is here, and the actions are all the actions we're going to take. So basically the whole MDP is referenced inside of here and allows us, by determining utilities, to always know what's the best action to take. Well, it's the one that's going to maximize the utility. So if we can figure out the answer to this equation, the utilities of all the states, we perforce know what the optimal policy is. It becomes very easy. So we've sort of taken all that neat stuff about MDPs and stuck it in a single equation. Bellman was a very smart guy.
So he's the same Bellman from the Curse of Dimensionality?
Yes,
Cool.
there can be only one Bellman. Actually, are there any more Bellmans? I don't think so. I think that they retired. It's like retiring a jersey. They retired his name.
I could have sworn that I saw one at the last hotel that I went to.
It's probably the same one. Oh, I get it. Hotel Bellman. That's really good.
There we go.
Okay, good. Well, so now that we've killed that as much as we could, let's see if we can actually solve this equation. Which, since this is clearly the key equation, since it has a name. Okay.
Yeah, that would be cool, especially because it looks like if you could solve this, you could solve it, right? Because then you have u. You can just plug the u in and get the u out.
Right, and once you have the u in and you get the u out, then you got the policy.
Right.
For you.
It's always been for you.
It's for us, Michael. It's for us.